Today, let's talk about a classic interview question. Find all anagrams in a string. Here's the problem. You're given two lowercase strings, s and p. Your task is to find all starting indices in s where a substring of length equal to p is a permutation of p. In other words, the substring contains exactly the same characters as p, just possibly in a different order. For example, if s is the string you see on the screen and p is abc, the answer is 0 and 6, because the substring starting at index 0, cba, and the one at index 6, bac, are both permutations of abc. Another example, if s is abab and p is ab, the answer is 0, 1, and 2. You'll notice this problem is very similar to the previous one about permutation in string. The difference is, this time we need to find all matching positions. The sliding window approach from before still works, but today we'll use an optimized algorithm. We'll combine a fixed-length sliding window and frequency arrays and add a match counter so we don't have to compare two arrays of length 26 every time. Here's the core idea. Since we're only looking for substrings with the same length as p, the window size is fixed. We use two arrays of size 26 to store character frequencies. The need array records how many times each character appears in p. The window array records the character frequencies inside the current window. We also introduce a variable called valid, which represents how many characters currently have exactly matching frequencies between window and need. As the right pointer moves to the right, we add the new character into the window and update valid if its frequency now matches need. When the window length exceeds the length of p, we shrink from the left and update window and valid again. Whenever the window length equals p and valid equals need count, we found an anagram and record the left pointer index. The benefit of this approach is that valid replaces repeated comparisons of all 26 characters, which improves performance. Let's walk through the first example. First, we build the need array. Characters A, B, and C each appear once, so we need to match three character types. The right pointer starts at index 0. We read C. The count of C in the window becomes 1, which matches need, so valid increases to 1. We read B. Its frequency also matches, so valid becomes 2. We read A. That matches as well, so valid becomes 3. Now the window length is 3 and valid is 3. We found the first anagram, so we record index 0. The right pointer moves forward and reads E. Since E is not in need, valid stays the same. The window length now exceeds 3, so we shrink from the left. Before removing C, its frequency was matching, so valid decreases to 2, then we decrease the window count of C. Since valid is no longer 3, this window is not a match. The window continues sliding. When the right pointer reaches index 8, we read C again. Its frequency becomes 1, matching need, so valid goes back to 3. We then shrink the left side. Before removing A, its window frequency was 2, which does not equal the needed count of 1, so valid stays unchanged. After shrinking, the window is BAC, valid is still 3, and we find the second anagram at index 6. The right pointer moves to the end and reads D. It doesn't match anything in need. We shrink once more, and the algorithm finishes. The final result is indices 0 and 6. Now let's look at the Python implementation. First, we count the character frequencies of P and store them in the need array. At the same time, we calculate need count, which is the number of unique characters that need to be matched. The main loop has 3 steps. First, expand the window. Read the character at the right pointer, update the window frequency, and if it now matches need, increment valid. Second, shrink the window. When the window length exceeds P, move the left pointer to the right. Before removing the character, if it currently matches need, decrement valid first, then update the window frequency. Third, check for a match. If the window length equals the length of P and valid equals need count, we record the left pointer index. The time complexity is O of n, where n is the length of S. The space complexity is O of 1, since we only use fixed-size frequency arrays. Using the valid counter lets us check matches by comparing two integers instead of scanning 26 elements every time, which makes the algorithm more efficient. The trade-off is slightly more complex logic to maintain valid during expansion and shrinking.